Okay, so welcome back. So today we can finish lecture 6, and lecture 7 is talking about discrete Fourier transform, which will take probably one to two lectures, and lecture 8 is the sampling. So we should be able to finish lecture 8 after at around April 5 or 6. So maybe we'll have midterm 2 around that time. So we will figure out the exact schedule for midterm 2 when we go to lecture 8. Yeah, but I think the estimated time would be around April, I don't know, 5 to this March. Yeah, maybe around April 5th or 7th. And make sure you finish all the homeworks in time and submit them in time. Okay, so we talked about Fourier transform last time, and there's a lot of properties associated with Fourier transform, especially the time shifting property, frequency shifting property. And then we also have this differentiation property. These are probably the most important properties of Fourier transform. And the other one is the convolution property. So with this convolution property, we can directly apply Fourier transform to analyze LTI systems. Because for LTI system, we know that the input and output relation is given by this convolution equation. As output is equal to the input convolution with the impulse response of the LTI system. Now this happens in the time domain, but if we transform everything into the frequency domain, we can get rid of the convolution on the right-hand side. So after taking Fourier transform on both sides, we ended up with, in the frequency domain, the spectrum of the output signal is basically the product of the spectrums of the input and the system response. Okay, so in the frequency domain, we only need to deal with the product instead of convolution. And this gives a very fundamental tool to analyze LTI systems. Well, instead of looking at convolution in the time domain, we can analyze the system equation in the frequency domain. Okay. And after that, after we figure out the spectrum of the output signal, we just need to do an inverse Fourier transform, and we can get the signal back into the time domain. So when we analyze these systems using Fourier transform, we can always, now for standard signals, we can always refer to to that table of Fourier transform pairs, so that we don't have to calculate the Fourier transform or the inverse Fourier transforms by hand every time. So for example, I think last time we went over this, we went through this example. We have a standard LTI system where we are given the input signal. It's a standard exponential, causal exponentially diminishing signal. And we are also given the impulse response of the LTI system, which is also exponential signal. Now the goal is to find out the output signal, YT. Now here we can do it in the frequency domain by avoiding the convolution. So the idea is to basically leverage the system equation in the frequency domain. So this is the system equation in the frequency domain. So basically to evaluate the spectrum of the output signal, we just need to in the first step, we need to figure out the spectrum of the input and the system impulse response, respectively. So the first step is to calculate the Fourier transform for both the input and the system response. And since the signals are given already, and they are in a standard form, so you can look into that table of Fourier transform pairs, and you can see that these exponential signals, they have their Fourier transform takes this specific form. And then having these spectrums, we simply multiply them together. And this gives the spectrum of the output signal. So the last step is to figure out to do an inverse Fourier transform and figure out which signal corresponds to such a spectrum. So notice that this is a big fraction number, so we can do a standard partial fraction expansion, decompose this into two smaller fraction numbers. And then for each of them, you look into that table, you realize that, for example, this one corresponds to such a standard exponential signal. And similarly, for the second fraction, for the second spectrum, it corresponds to the other, which is also exponential signal. So you can see that in the entire process, you don't have to, as long as the signals that are given are standard signals, you don't have to calculate the Fourier transform or inverse Fourier transform by hand. You just need to refer to the table and figure out the transformation pairs. Okay, so this is how you solve this type of problems in the homework and also in the exams. Typically, you can refer to the table, and in the exams, I will provide you the list of Fourier transform pairs so that you can utilize the existing results. Okay, so here's another example where we analyze a very specific LTS system characterized given by the differential equation using the Fourier transform. So for this LTS system, the input and output relation, which is also the system equation, is given in this form. Okay, this is a standard differential equation, partial differential equation. On the left-hand side, you have, this is a zeroth order derivative of the output. Now this is the first order derivative, second order derivative of the output. So it's a linear combination of different orders of derivatives of the output signal. And on the right-hand side, you have the same thing for the input signal. But for the input, we only have derivatives up to the first order. Okay. So in general, it's a differential equation, and we need to, so we want, okay, the problem is that given such a system, we want to find out the impulse response, HT, of such an LTS system. So the input and output relation is completely given, it's fully given. So there should exist a corresponding impulse response of this LTS system. And if you do this in the time domain, it is very challenging, because in the time domain, we know that for an LTS system, YT equals to XT convolution with HT. Okay, now you want to figure out this HT, given that this XT and YT satisfies such a complex partial differential equation. So this is this is unclear, because here we need, here in this system equation, we have lots of higher order derivatives Well, in the standard LTI system equation, we have this convolution. So it is not clear how to figure out this HT from this system equation. But if we look at this in the perspective of the frequency domain, things will become much more clear. So if we take Fourier transforms, now everything is in the frequency domain, the signals becomes the corresponding spectrums. And here we have multiplication instead of convolution. Which means that, so from this equation, we can already solve for the impulse response. So the spectrum of the impulse response is basically the spectrum of Y divided by the spectrum of X. Which means we just need to figure out this ratio, capital Y over capital X. And then this will give us the spectrum of the impulse response. Once we have this spectrum, we do an inverse Fourier transform. We can figure out the corresponding HT. Okay. So the question is, how do we obtain such a ratio, a spectrum ratio, from this system equation? And turns out, if we transform this into the frequency domain, it will be much easier. So we directly take Fourier transform on both sides of this system equation. And leveraging the differentiation property of Fourier transform. So for the first term, we have, this is the second order derivative of YT. So the corresponding Fourier transform is given by the spectrum of Y multiplied by j omega to the power of 2. Okay. So in the frequency domain, differentiation, higher order differentiation simply becomes a simple scaling of the spectrum. Now, similarly, you do this for all the terms. Like for the second one, is 4 times the Fourier transform of this first order derivative. So the Fourier transform of this first order derivative is given by the spectrum of Y multiplied by j omega. This is by the differentiation property of the Fourier transform. So here you have 3YT. Now after doing the Fourier transform, you have 3 capital Y. And on the right-hand side, you have the same thing. This is the first order derivative of xt. So you end up with the spectrum of X multi-scaled by such a coefficient j omega. And then this one, 2xt, is transformed into 2 times capital X. Okay. So now, after taking Fourier transform, the system equation is now in the frequency domain. And you can see that you completely get rid of the higher order differentiations. And instead, you only have a simple equation, a linear equation with regard to the spectrum of Y and spectrum of X. And they are just scaled by different constant coefficients. So you reorganize this equation, rearrange all the terms, you end up with a very simple equation, which is a complex number times capital Y equals another complex number times capital X. And from this equation, you can figure out this spectrum ratio. Capital Y over capital X is given by this complex fraction number. And this Y, capital Y over X, as we discussed here, is exactly the spectrum of the impulse response. So in the end, starting from the time domain system equation, differentiation equation, right? We do a Fourier transform and followed by a very simple algebra. We derive that the spectrum of the system impulse response is given by such a complex number. So in the end, we can conclude Hj omega equals to is specifically given by this one. So this is the spectrum of HT. And then as long as this spectrum is given, you can do an inverse Fourier transform to figure out the time domain impulse response. How do we do that? So again, we do a standard partial fraction expansion because this spectrum is given in a very complex form, right? It's a very big fraction number. So we do a standard partial fraction expansion. We will talk about this later in the following slides if you are not familiar with partial fraction expansion. But following a standard technique, you can decompose such a big fraction number into, in this case, into two smaller fraction numbers. Okay. And if you look at this simplified form, you have two simple fraction numbers. And looking at each of the fraction number, it falls into the standard Fourier transform pair of exponential signals. So let's go back to this one. See, you can see that whenever you have a spectrum that looks like this, it's a constant divided by j omega plus a. So let's copy this one here. Just E negative a t ut. This signal corresponds to such a spectrum. Okay, so given this pair, now we have Hj omega equals to 1/2 over j omega plus 1 plus j omega plus 3. Okay, so for each of them, this fraction number falls into this standard form. So we can directly refer to this Fourier pair and conclude that. So if you compare these two, you can see that looks like this small a should be 1 here, right? And here you have 1 in the numerator, but here you only have 1/2. So you can view this as a simple linear scaling, and Fourier transforms are linear. So you end up with, you can conclude, you can first rewrite this as 1/2 times 1 over j omega plus 1. And this part exactly corresponds to the standard form. And this is just a scaling coefficient. If you do inverse transform, this coefficient will be preserved because the transform is a linear operation. So you end up with this coefficient. And now this spectrum doing an inverse transform, following this table, you have now this small a corresponds to 1. So you have E negative t ut. Okay. So this is only the first fraction number. So for the second one, you do the same thing. You ended up have 1 over 2. Now the small a is equals to 3. So you have e to the power of negative 3t ut. Okay. And this is the system impulse response. Right. So once you figure out the spectrum, the inverse transform, in most of our homeworks and the exam problems, it can be you can leverage the existing table to calculate the inverse transform. Okay, therefore we conclude that for such a LTI system, described by such a higher order partial differential equation. The corresponding impulse response is given by such a HT signal. And you can see the power of Fourier transform. So once you transform everything in the frequency domain, you can get rid of convolution, get rid of differentiation and integration. So that is why in many cases, it is very convenient to analyze signals and systems in the frequency domain. Okay, now the key question is how do we do that partial fraction expansion? So here's an illustration. So for example, once you end up with such a complex fraction number, well, in the numerator, you have a product of two terms, two first order terms. This is s plus 2, s minus 3. And in the numerator, you have a single first order term, 7s minus 6. And we can figure out, we can figure out the decomposition by by setting up a general coefficient that are to be determined later. So for example, we can, without loss of generality, we can say that this big fraction number equals to the first factor in the denominator over a constant plus the second factor in the denominator over another constant. So the question is how can we figure out these two constants K1 and K2? Well, we can determine their values by looking at by comparing the specific values of this equation at different locations of S. So for example, to determine the coefficient K1, we simply multiply both sides by S plus 2. So we can get rid of the denominator here and end up with a constant K1. Okay, so multiply both sides by S plus 2. And then, so doing that, the left-hand side becomes this one, 7s minus 6 over s minus 3. So s plus 2 goes away. And the right-hand side becomes this one. So you can see we have a K1 here. And then we can evaluate both sides at s equals to -2, which is the root of this factor s plus 2. So you set s plus 2 equal to 0, which gives s equals to -2. And then you evaluate this equation on both sides at s equals to -2. And you can see that this factor will always become 0 because s plus 2 is multiplied in the numerator. So when evaluated at its root, this numerator becomes 0. So this term that contains K2 will goes away. So this is 0. So you only have K1 equals to the left-hand side, which will give you the numerical value for K1. Okay. So you plug in s equal to -2 into this fraction number, you can figure out K1 equals to 4. And then we will repeat this process to determine the value of K2. Okay. So to determine K2, you simply multiply both sides by the new denominator of K2, which is s minus 3. After multiplying by s minus 3, then you evaluate the entire equation at the root, the corresponding root, s equals to 3. By doing so, you will find that the terms that involve K1 will become 0. So you only have, on the right-hand side, you only have K2. And this will conclude that K2 equals to 3. So by following this standard process, you can figure out the values for K1 and K2. So, and in this case, K2 equals to 3, K1 equals to 4. So you conclude that that big fraction number can be decomposed into these two smaller fraction numbers. Okay, we have a question. Will we have to do this with complex numbers? The answer is yes, probably. But I think there's no difference whether this is real number or complex number. So you always follow the. So here you can imagine that S is can generally be a complex number. So there's nothing different between complex and real numbers. You always multiply both sides by one of the denominator factors, and then follow the standard process. So let's go over some examples. So here are two examples, and we want to use partial fraction expansion to decompose them into smaller fraction numbers. So for the example 2, so normally, I mean, in the homeworks and in the exams, example 1 is sufficient. Okay, so as long as you can handle example 1, you should be able to work out the homework and the exam problems. But let's look at the more complicated example 2 and example 3. Well, here you just follow the standard steps because the denominator is already in a factorized form. You have s plus 2 square times s plus 3. So what you do is you can actually do this step by step. I will first take out one factor. Okay, so this is equivalent. And then I can follow the previous. I can follow the standard steps of example 1. Right? We have the denominator is a product of two first order terms. The numerator is a single first order term. Okay, so we have same story here. So for this one, you can follow the same process, and then you will end up with. So this fraction number can be decomposed into k1 over s plus 2 plus k2 over s plus 3. Well, the value of k1 and k2 can be identified by following this process. So after that, you almost have the decomposition. So the first one, you get k1 over s plus 2 square, and this is already the simplest form. You cannot decompose it anymore. And the second one, you have k2 over s2 s plus 2 times s plus 3. And this one, you can again follow standard steps to decompose it into into these two. Okay, or you can, let's actually follow the, okay, follow another easier step. So we have 2s. We can actually directly decompose it into this form and then just compare the coefficients. So let's actually do this. So I can propose this fraction number can be decomposed by k1 over s plus 2 square plus k2 over s plus 2 plus k3 over s plus 3. Okay. Here, because s plus 2, this factor has second order, so you need to have second order, both second order and first order expansion. And then you follow the standard steps to evaluate k1, k2, k3. For example, to get k1, you can multiply both sides by the factor s plus 2 squared. Right? Because the denominator on k1 is s plus 2 squared. And once you do that, the left-hand side becomes this one, and right-hand side is k1 plus k2 s plus 2 plus k3 s plus 2 squared s plus 3, right? And then you evaluate both sides. At the root, which is s equals to -2. Now, when s equals to -2, you will figure out this becomes 0, this becomes 0. So these two terms become 0. Right? Because s plus 2, there's at least one factor of s plus 2 in the numerator, which makes them vanish. And then k1, so you end up with k1 equals to this fraction number at -2. So if you plug in -2, you have 5 minus 4, which is 1, and 3 minus 2, which is 1. So k1 equals to 1. Okay. So this is for k1. For k2, you do the same thing. You multiply this equation by s plus 2 only. Let me see. Here is a little bit different. If you multiply by s plus 2, then you have, so this part cannot goes away.
I think the first fraction, does it have a square, the k1? Or is it just over s plus 2?
We have to have this term here. Otherwise, if we don't have the first term, like these two terms will only give us s plus 2 multiplied by s plus 3 in the denominator, right? We will not have s plus 2 squared. Let me think about this. Yeah, I think we can figure out k1, k3 is okay. Once you multiply both sides by s plus 3, you can figure out these two will goes away. So you can figure out k3. But this one is something special because it is the first order of s plus 2. So Of course, once you figure out K1 and K3, you can go back and solve for K2. But here I'm looking for a standard process. We multiply by Ks plus 2, then we still have K1 over S plus 2 here. And then you cannot evaluate at the root because then this will become infinity. And also this will also become infinity. So I guess K2 may be equal to 0. Yeah, in this case, K2 should be equal to 0. Yeah, let me figure out K3 first. For K3, you multiply, we can do this quickly, multiply by S plus 3. So you have evaluated at S equals to -3 by the root of this one. So this gives us K3 equals to -1 over 1. This is -1. Okay. So this is 1, this is -1. And then you can go back and solve for K2. So you have 1 over you have this one. And now you put everything to a big fraction number. So this will have S plus 3. And this have K2 S plus 2 times S plus 3. And this one has -1 times S plus 2 squared. We just need to make the numerator look like 2s plus 5. So if we keep simplifying, yeah, it's a first order, because the numerator has to be first order. So K2, I guess it has to be 1. Otherwise, the S square cannot be canceled out. But let's see. Yeah, okay, let's verify. Yeah, it seems that we have to let K2 to be 1 in order to cancel the second order term. So we have, then the numerator becomes this one. So this is 1. So we have S squared plus 6 plus 5S. And then minus this one, minus S squared minus 4 minus 4S. These two cancels. 5S minus 4S plus S is 2S. 3 plus 6 minus 4 is 5. Okay, it's 2S plus 5. Yeah. So by comparison, you can tell K2 equals to 1. So in the end, K2 equals to 1. K2 equals to 1. But we won't have these higher order terms in our exam. We may have something like example 3. So let's look at this one. For example 3, the challenge is that this numerator and denominator, they are not completely they are not completely factorized. So we need to factorize them first on the S. So the denominator, right, S plus 4 is the simplest factor. But for this one, S squared plus 5S plus 6, this can be further factorized. So you can see that I can factorize 6 to 2 times 3. Well, 2 plus 3 equals to 5. So that gives us this factorization. Okay, so these two product will equal to this big number. And then we have S plus 4. And then you can see that the denominators of order 3, because we have 3 first order terms, and numerator has order 2. So you can propose to decompose it into K1 over S plus 2, K2 over S plus 3, and K3 over S plus 4. Okay. And then the rest of the story is the same. To figure out K1, you multiply both sides by S plus 2, and then evaluate both sides at S equals to -2. To figure out K2, we do the same thing with S plus 3 and S plus 4 for K3. So you don't have to factorize the numerator. Only the denominator is the key part.
Do you think that we'll have problems that we'll have to complete the square on the bottom?
For this one?
Not for that one in particular, but in general. So I remember there was some rule about the number that gets added to the third term. If it's positive in the denominator, then it's a complex number or something like that.
Are you trying to make this a complete square term?
I've seen examples before where impartial fraction decomposition, where in the denominator, if we have to complete the square, there was some rule about that number that we have to add to the third term. If it's positive, then it ends up being a complex number or something like that.
Yes. So basically, I think, so the basic idea is to solve this, to set this term equal to 0 and solve for its two roots.
Mm-hmm.
Right? And you can see that -2 and -3 are two roots associated with this equation. Yeah. And in this case, for this specific expression, for this specific term, the two roots happen to be real valued. But in general, for example, you have if here we have S squared plus 1 only, and the roots will be the complex unit J. Yeah. And then this will become S plus J and S minus J. So you can still do the partial fraction expansion.
Do you think we'll have any problems like that in this class?
We probably don't have something like that. Yeah. So
okay,
here you
just checking.
Yeah, here you can check. You can view the S. This S can already represent any complex number. Yeah. So in general, the entire equation, the entire function, this is a function of S. The value of S can be any complex number, not necessarily real numbers. But I think for these examples, you don't have to deal with the complex unit J.
Okay, sounds good.
Yeah, so in general, you have to, the idea is to the idea of factorization is to basically solve this equation, set this one to 0, solve for the two roots. And then once you have the two roots, you will have the factorization. But in this case, well, it is kind of straightforward to tell the factorization because 6 can be decomposed into 2 and 3. And the summation of these two factors happen to equal to 5. So in this case, this tells you that 2 and 3 are the two roots of this equation. Yeah. But anyway, it's a matter of factorization. So I think in the problems, the factorization should be relatively easy to tell. Okay, so this is the partial fraction expansion. So once you figure out, when you do the Fourier transform, you analyze the LTI systems. Once you figure out the spectrum of the target signal, it could be either the output signal or the system response. So once you have this big fraction number, you do a partial fraction expansion, decompose it into simpler ones. And for the simpler ones, you can easily tell from that table, Fourier transform table, you can easily tell the inverse signals associated with each of the spectrum, each part of the spectrum. So in this case, for this specific spectrum, after the partial differential expansion, partial fraction expansion, this specific spectrum is associated with this standard exponential signal from that table. Okay. So in this way, you can completely avoid calculating Fourier transforms or inverse transforms by hand. Okay. That's the idea. For this type of problems, you don't have to do any calculations. You don't have to do any Fourier transform calculations. So we can skip this part. This is basically say we can rewrite Fourier transform by replacing the angular frequency by the frequency 2 pi f. Okay. So there are some special cases of the Fourier transform. So for example, here we can consider a frequency response to a very simple input, sinusoidal input. Okay. So assume that for an LTI system, we input a very standard cosine or sinusoidal signal, A cosine omega t plus theta. And suppose we are given the impulse response h j omega of the LTI system. So basically, this capital H is the Fourier spectrum of the impulse response ht. Okay, so this is the definition. So we are given the frequency impulse response. We are given the response in the frequency domain. So before lecture 4, when we talk about LTI systems, we always tell the frequency response is always given in the time domain. We have as ht, right? And then we do convolution to figure out the output. But here, sometimes we also give the frequency response directly in the frequency domain. Okay, so given this capital H, and suppose it is conjugate symmetric, it satisfies this conjugate symmetric property, which means that the underlying impulse response signal is a real value signal. But we have a property of Fourier transform saying that if a signal is real valued, then the corresponding spectrum satisfies this conjugate symmetry property. Okay. So given such an input and given such a system frequency impulse response. The output can be shown to take this form. So the output is simply, it takes the similar form as the input signal, with the only difference that first of all, the magnitude A is amplified or scaled by the magnitude of the system response at this particular frequency. But it is A times the magnitude of the response, capital H, evaluated at this particular frequency omega naught. Now this omega naught is the frequency of the input. This is very intuitive because the input is the input signal is only located at a particular frequency omega naught. If you draw the spectrum of cosine signal, it is a pair of impulses located at omega naught and or negative omega naught. So this means that when you pass these signals through such a LTI system, the signal will be scaled by the corresponding system frequency response at that particular frequency. Okay, so the magnitude is scaled in such a way. And moreover, the phase part, theta, will also be shifted by the corresponding phase at that particular frequency response. So in general, H omega, so you can think of H omega this response, system response at this particular angular frequency omega naught. This is a complex number. So if you think of this in the polar form, then the magnitude of this complex number will be used to scale the magnitude of the input, whereas the phase of this complex number will be imposed on the phase part of the input signal. So you can see how the system reacts to such a standard sinusoidal signal. So both the magnitude and the phase will be modified by the corresponding system response at this particular frequency. And the way to show this is to following the standard approaches. Like you do a Fourier transform, and then you figure out the spectrum of YT, and then you do an inverse Fourier transform. But after many lines of derivations, you can end up with this very intuitive explanation. And the reason that we care about the response to standard sinusoidal signals is that many signals can be decomposed into sinusoidals. For example, based on this previous characterization, based on this slide, where we talk about the output corresponds to a standard sinusoidal input, we can further look at the output to a periodic real value signal. First of all, if we consider periodic real value signal, now from the Fourier series, we know that every periodic signal can be represented into a Fourier series. Right? So this is the Fourier series representation, periodic real value signal. And then in that lecture, we also showed that this one can be, if the signal is real valued, periodic and real valued, then we can combine the positive index, the terms with positive index, with the terms with the corresponding negative indexes, so that this Fourier series can be written into a summation of sinusoidal series. Okay, So basically, every periodic real value signal can be written in this way into a combination of standard sinusoidal signals. And then in the previous slides, we showed that we have a understanding of the response to each of the sinusoidal signals. So therefore, by leveraging the linearity of Fourier transform, we can conclude that for such a periodic real value signal, if we look at the signal in the decomposed perspective, then the corresponding output is basically since in this summation each term corresponds to a standard sinusoidal signal, so we can leverage the result from the previous slides, right? So each of the sinusoid will be output in this way. So here is the same story. Each of these cosine signal will be amplified. The magnitude will be amplified by the corresponding system response at this particular frequency. And the phase will also be shifted corresponding. Yes, I think the textbook has a appendix for that. Yeah, if you need more examples, you can refer to the appendix of the textbook. And thanks for pointing that out. So here, I think the idea here is to show that when we introduce Fourier transform, if you look at the title of this lecture, it is for aperiodic signals. Right? But turns out that for periodic signals, we can still analyze the output, corresponding output using Fourier transform. But we just need to, for periodic signals, we will need to first decompose the signals into Fourier series. And then for the Fourier series, each of the eigen signals is a exponential or sinusoidal signal. And we know the response. We know the system response to these standard sinusoidal signals in an LTS system. So this is how we analyze the response to a periodic signal. So the last part is related to, okay, it's actually talking about filters. Well, we want to develop an ideal low-pass filter. So ideal low-pass filter is that we will talk about this later in the lectures 8. Yeah, but this is another application of Fourier transform. So idea of low-pass filter is that for some like audio signals, you have, if you look at the spectrum, of an audio signal, it may have some high frequency components, and that those could be induced by some additive noise. So you want to, sometimes we only want to keep the low frequency part. But the idea is very simple. You simply generate an ideal low pass filter. Which is a window function in the frequency domain. Well, the window length is bounded by B and the negative B. And this B is the cutoff frequency you want to have for this low pass filter. So this is by design. This P is by design. So in general, the mathematical expression for such an ideal low-pass filter is like between this frequency band negative D to B, I want the filter to have to be, I want the response of the filter to be 1 multiplied by a phase part. And beyond that, the response should be strictly 0. Then if you can have a LTI system with such a system response, and then you input any signal X, then by the LTI system equation in the Fourier domain, right, you have the output equals to input times the system response in the frequency domain. And then multiplying any input with such a low pass filter, the effect will be that you only preserve the low pass components of the input, and you can filter out all the high frequency components. And this is the most general form for an ideal low pass filter. So within this band, the filter is 1 times a standard phase part, because this phase part will not affect the magnitude response, right? So within this band, if you look at the magnitude of this response, it is always constant 1. And then given this mathematical, this is the mathematical expression for an ideal low pass filter, and then we can figure out its corresponding time domain representation. So doing an inverse Fourier transform, from that list of table, we have 1 transformation pairs corresponding to this window functions. So we can see that inverse transform in the time domain will give a sinc type of signal. So it turns out to have this standard expression. So it's a scaled sinc type signal. And because of the frequency modulation, because of this modulation factor in the frequency domain, right, by the frequency shift property. No, actually by the time shifting property, right? A shift in the time domain will lead to such a phase shift in the frequency domain. So basically, when you do an inverse transform, this phase shift factor will induce a time shift factor in the time domain. Or you can say that, well, from that table, we know that 1 corresponds to this sinc type of function without this delay. And then by the time shifting property, we can conclude that adding such a time shifting, introducing such a time shift will result in a phase shift in the frequency domain. So this is why we have tau d in the time shift in the time domain as time shift in time domain. So this means that in order to generate such an ideal low pass filters LTI system, you need to create an LTI system with this specific type of impulse response. Okay. And this is in general not very hard to realize in practice, because this HT is a sinc type function, and that this function looks complicated in the time domain. We have some approaches to approximately develop such a low-pass filter. I think our lab 4 is to develop the low-pass filter, approximate low-pass filter, by concatenating many complex units. Okay, so this is the lecture 6. So we talk about the Fourier transform the continuous time Fourier transform and its applications to analyze LTI systems or partial differential equations.
I have a quick question.
Yes, go ahead.
You mentioned that the table of transform pairs would be provided for an exam. Would we also be able to have the table of the properties?
Oh, yeah, that's a good question. Well, since there are a lot of properties, probably 6 to 7 or even more, I think I will provide some of them that will be related to the problems or the exams. But I suggest you always maybe copy all of the properties on your reference note. Yeah. Yeah, I will not provide all of them, but maybe like some of the time shifting, frequency shifting, or the convolution property, like these key properties. The other properties, I think you have to write them down on your own notes. But I think we will only touch part of the properties.
Okay, sounds good. I just noticed in the book there was a table 4.1 that had the properties that was right before table 4.2 that had the transform pairs. It's page 328, 329. So I was just wondering.
Yeah, you can utilize that table too. You can put that on your reference sheet. Yeah.
Okay, sounds good. Okay, thank you.
Yeah, and we have about 10 minutes left, so we can briefly talk about the discrete time Fourier transform. So remember, we have continuous time Fourier series and discrete time Fourier series in the lecture 5 or 6. And there are some differences there, like because when we restrict the time index into discrete, we only need a finite number of bases. That is for the Fourier series. Here for the Fourier transform, it's the same idea. Most of the definitions properties are exactly the same as continuous time Fourier transform. But because we are now looking at discrete time, there are some subtle differences. And again, the discrete time Fourier transform is for analyzing aperiodic discrete signals. So the discrete time Fourier transform is kind of like a discretized version of the continuous time Fourier transform, where we have, since the signals is now discrete, so we have xn instead of xt. And because n is discrete, so we have summation over n instead of integration over t. So this is the only difference. Otherwise, they look the same. They have the same structure. And e to the power of negative j omega n. And a key difference is that because it's discrete, because of the discrete nature of the time index, that makes the corresponding spectrum a periodic spectrum with a fundamental period 2 pi. So basically x e j omega equals to omega plus 2 pi. Why? Because you plug in, okay, with this additional 2 pi, right? So you will have an additional factor e to the power of negative j 2 pi n. And because n is a integer in the discrete time domain, right? So e to the power of negative j 2 pi n is always 1. Right? If this n time index is integer, this factor is always 1, no matter, right, as long as n is integer. So integer multiple is integer times 2 pi by the Euler's formula, right? This is 1. Therefore, in discrete time domain, the spectrum corresponding Fourier transform has a periodic structure. But we don't have this property for the continuous time domain because there the time t is not necessarily integer. Okay, so this is the key difference between discrete time Fourier transform and the continuous time Fourier transform. And because of this periodic structure, it implies that it is sufficient to characterize the spectrum within one period, right? Because it is always periodic with period 2 pi. So if you visualize the spectrum doing one period is enough. And because of that, the inverse discrete transform is defined well in a similar way as the inverse continuous time Fourier transform, but because of the discrete, because of the periodic nature, that integration in the inverse transform is taken over one period from negative pi to pi. In the continuous time inverse Fourier transform, we have to integration over the entire frequency domain. Other than that, the structure is exactly the same as the continuous time. And I will skip, this is the proof of the inverse transform to show that it is indeed a valid inverse. But I think I will skip that. Okay, and the computing, okay. Computing the DTFT of the discrete time signals is very standard. And because by definition, this DTFT is defined in, because now we are dealing with aperiodic discrete time signals. And in this definition, we have the summation. So most of the time when we compute DTFTs, we will need to evaluate summations of infinite series. For example, if you want to evaluate the DTFT of such a exponential signal, it's causal because of this UN. So by definition of DTFT, right, this is the standard definition of DTFT corresponding to this signal. And because of this UN, we can basically restrict the summation within the positive time domain. So we can get rid of this UN, and instead, this n will start from 0. Okay, so now this is a summation of infinite series, and this is a geometrically diminishing infinite series. So we can rearrange the terms so it is more clear in this form. It's a summation over n, infinite summation over n. Well, it is a times e to the power of negative j omega. It's a certain complex number to the power of n. Okay, so it's a summation of infinite series. And because the magnitude of A is strictly less than 1, so we have the magnitude of the inside, the entire complex number is still strictly less than 1. And then we can conclude that this series is convergent and takes this simple form. So we can have this, we can leverage this infinite summation series formula. If this A, if the magnitude of A is less than 1, then this series converges to 1 over 1 minus A. Now in this case, this A is actually A times e to the power of negative j omega. But this term only modifies the phase part of the complex number A. It doesn't affect the magnitude. So again, we will have the magnitude to be smaller than 1. So applying this formula, we end up with this result. So basically, when you compute DTFTs, you will always deal with summations of infinite series. And I think this is another example, but I think I will leave for the next lecture. But as you can see, for the DTFTs, they have pretty much the same structure of CTFT. And the only difference is that we are now in the discrete time domain, and everything will be discrete. But we will see later that this DTFT preserves almost all the properties, important properties of CTFT. So we can still utilize DTFT to analyze discrete time LTS systems or discrete time difference equations. Okay, instead of differential equations, we have difference equations in the discrete time. Yeah, okay. So I think I'll stop here today. So after, so the next lecture, we should be able to finish lecture 7, and we need another lecture for lecture 8. So Thursday, we can probably finish lecture 7, and next Tuesday, we can probably finish lecture 8. So the worst case is that next Thursday, next week, we will finish lecture 8. So you should start to plan finishing the homework 6, 7, and 8 in time as we proceed. And if we finish lecture 8 at 24th, and then we do a review lecture 29th. Okay, and then probably we can, yeah, we'll have midterm 2 either on 31st or 5th, April 5th. Okay, so let's discuss this in the next lecture. So the midterm 2 will be either on 31st or April 5th. I think maybe, yeah, we will talk about this later. Maybe April 5th is a better choice, so you can have more time to review the materials.
Agreed.
Yeah. And on the 31st, we can leave it for office hours if you like. And then 5th, we have midterm 2. I think we'll have enough time for the lecture 9 and 10. Okay. Okay, sounds a feasible plan. Okay, so if you don't have any questions, we can end early. We can end early today, and I will hold office hours over the Zoom. Okay, you can connect to my own meeting room. Okay, I will see you on Thursday. Thanks, everybody.